I think it's
it should be.
Okay,
I think it's.
it is time once again for us to have a seminar. It is that time of week. We've made it. So this week we have Susan Clark, who will be giving our seminar. Susan did her PhD at Columbia and then moved to the IAS for a few years and then proceeded to get a faculty job at Stanford. So that's where she is now. She's going to tell us a little bit about actually how magnetic fields work, which is exciting because I still don't understand what this does.
Perfect. Thank you very much. I love that. And I know that many people feel that way about magnetic fields, but I hope that today will at least pique your interest, if not make you a devotee. So today I'm going to talk about magnetic fields and also morphology, what we can learn from the shape information of observations that we have of the ISM. And this is work with many people. My group at Stanford is the Cosmic Magnetism and Interstellar Physics Group. It's the shortest name I could possibly think of. It tries to cover the breadth of the things I like to think about. I won't do any justice to what all of these awesome people are working on, but you should check out our website and their individual pages for lots more. What I want to talk to you about today are magnetic fields, which we know are absolutely ubiquitous in the universe. And you may often think of magnetic fields as being associated with particular compact objects, stars, or the planetary magnetic field that is keeping us all safe from solar radiation right now. But as we know, galaxies themselves are also home to diffuse, large-scale magnetic fields that really pervade the space between the stars, the interstellar medium, the ISM. I will talk today mostly about our own Milky Way Galaxy, but we are really just beginning to map the detailed structure of magnetic fields in other nearby galaxies, especially with tracers like polarized dust emission, which is what all of these beautiful images are. And magnetic fields, we know, are not just everywhere, but just fundamentally change the character of the physics that sculpts whatever it is that you would like to study in your particular astrophysical environment. They play some poorly understood role in the formation of molecular clouds and eventually of stars. They really change the way that turbulence sculpts gas in the interstellar medium. Just making your hydrodynamics magnetohydrodynamic is an important physical change that changes the whole character of the way that your plasma works. They deflect cosmic rays and affect the propagation and therefore influence of cosmic rays on many different scales within galaxies. And yet we have these big picture open questions, not just what is the influence of these magnetic fields, but also what are their basic structure? What is the galactic magnetic field of our galaxy? What is the structure of interstellar magnetic fields on small scales in particular regions? And I know that some people have a visceral reaction to this topic. I love this particular quote, that the larger one's ignorance, the stronger the magnetic field. This is referring to this sort of joke in astronomy that if you encounter something you don't fully understand, just wave your hands and blame the magnetic field, right? That's sort of your ticket out. But obviously we would like to do better than that. This fundamental attribute of the physical universe is something that we would like to study and understand and incorporate into our physical explanations of different phenomena. And the good news is that, especially for those of us who study magnetic fields of galaxies and of the interstellar medium, is that we have a few different tracers that let us probe magnetism in different environments. We can measure Faraday rotation in the ISM. That's the change in the angle of linearly polarized light as it traverses the magnetoionic medium. Magnetized plasma, like our interstellar medium. We can measure
the synchrotron emission from charged particles accelerated in the galactic magnetic field and the polarized emission from that process. And there are two mechanisms that let us trace interstellar magnetic fields because of the presence of interstellar dust. The ISM is home to a lot of sort of submicron sized dust grains, not perfectly spherical on average. And on average, these dust grains find a preferred alignment between their spin axis, which is their short axis, and to the ambient magnetic field that they are sitting in. And so the fact that you have all of these spinning, elongated, magnetically aligned dust grains in the interstellar medium has two observable consequences. One is that these dust grains are going to preferentially absorb one component of the polarization of light in the optical or near infrared. And so if you observe a star, those wavelengths, you will measure typically a partial linear polarization that's not intrinsic to the star at all, but just imprinted by the magnetically aligned dust grains that starlight is filtering through on its way to your telescope. And then those same dust grains largely are also thermally radiating emission. That emission is also partially polarized, now in the orthogonal direction. So now 90 degrees from the ambient magnetic field orientation that these little dust grains are sitting in. And so this is the good news, right? With all of these different tracers, how is this still such a big open problem? Why have we not solved all of these questions about how magnetic fields influence the galaxy? Well, part of the answer to that is that these are pieces of a complicated problem. These are particular views on an ISM that is fundamentally multi-phase. And each of these tracers gives you information in general on a particular phase of the ISM and a particular component of the magnetic field structure. And so each of these is generally probing either the line of sight component of the magnetic field, the component parallel to your sight line, or the plane of sky component of the magnetic field. So whatever is orthogonal to your line of sight projected on the sky. And in different phases of the ISM. And so if for any particular question that you'd like to answer, putting together these pieces, or otherwise having a full three-dimensional understanding of even just the structure of the magnetic field, let alone its strength, is a complicated problem. And part of the good news here is that we have made some progress lately. I don't know how to get that to go away. We've recently mapped the full sky with Planck in 353 gigahertz polarized emission. This is a frequency that is dominated by this thermal emission from these magnetically aligned dust grains in the interstellar medium. And so this now very famous image, the color scale is giving you an indication of the column of dust. But the really eye-catching part of this image is the brush strokes, the Van Gogh-like swirls here. That is a visualization of what we measure from this polarized thermal dust emission, which is the line of sight integrated, plane of sky projected component of the magnetic field orientation. And so that is what is being visualized here in these brushstrokes. Beautiful to someone like me, but I know we also have a lot of cosmologists in the audience. And depending on who you ask, this is something much more horrifying, right? This is also a very bright, polarized foreground that is obscuring faint and wonderful signals that we would like to measure in the polarized cosmic microwave background. And so if this is your science, this is also quite relevant to you, as I'm sure you treat as inescapable. There's lots of very rich physics that is encoded or anticipated to be found in the polarization structure of the cosmic microwave background. And in the present day universe, we need to really understand the interaction of matter with magnetic fields in our own galaxy. We need to really understand this bright foreground signal if we want to disentangle the two and make our discoveries cosmologically. And so, you know, as the age-old saying goes, one person's treasure is another person's foreground. I tend to think of this actually as a real opportunity. It means that the better that we can understand the physics of the magnetic ISM, the better we can understand both this very bright polarized dust emission, also the synchrotron emission that's also quite bright at CMB relevant frequencies, the better we'll be able to disentangle this problem for cosmology as well. But today I want to talk to you about new angles on questions that we want to pose about the physics of the ISM and the magnetic fields that shape it. And the new angle, if I have to come up with some sort of umbrella description of it, is to use the very rich physical information that's encoded in the morphology of emission that we measure at various wavelengths. One of the awesome things about working on the ISM is that we often have spatially resolved images in different wavelengths, different physical tracers. We make pictures, right? And we know that these images are structured by the very complicated multi-scale physics that is shaping the ISM. These images contain a lot of detailed physical information, but we need ways of quantitatively extracting that information and using it to actually confront our ideas or our hypotheses about the physics with the observations. We want to move beyond, you know, simple 1 and 2 point measurements of or reductions of these data and really try and extract more of the physical meaning that's encoded here. And so one sort of theme, I think, of my research program here is how do we come up with quantitative descriptions of ISM morphology that let us pose new questions? And in particular today, I want to talk about new questions about phase and magnetic field structure of the ISM. And some of the data that we use to do this are 21 centimeter observations of the diffuse gas in our Milky Way Galaxy. So this is a video of data. These are observations from the GALPHA H1 survey with Arecibo. This is from your screen here, is about -1 deck at the bottom, about +38 deck at the top. So this is just the whole sky as visible from Arecibo and Puerto Rico, panning across your screen here, about 1/3 of the celestial sphere. And you'll notice in this video that there's also some sort of depth going on here. This is panning back and forth in wavelength, in Doppler shifted velocity of the galactic 21 centimeter line. And so what you're seeing here are structures pop out as you move basically in velocity space relative to line rest. Does that make sense? Beautiful, right? And so these are really striking. This is 4 arc minute data over 1/3 of the sky, tracing largely the diffuse and somewhat less diffuse ISM. This is emission from atomic hydrogen on 1 centimeter line over a huge swath of the sky. And certainly when I look at this, I am just struck by the real wealth of spatial structure here and just need to understand the physics that we can extract from the shape information in these data. And so I want to convince you today, or at least, put forward some evidence that the structure of these data, the spatial structure of this emission, encodes information on both the magnetic field and also the gas phase distribution. And we'll start actually with the magnetic field, maybe the simpler part of this argument. Because one of the first things that we did with these data years ago that sparked a lot of my present day research path is to measure just the orientation of linear structure in these images of neutral hydrogen emission. So you can write an algorithm that just quantifies the local orientation of linear structures, a particular algorithm, but what I'm about to say, you could come to the same result with a lot of different tools. And then you can compare that orientation of linear structure with a tracer of the magnetic field with, for example, the starlight polarization or the polarized dust emission from an experiment like Planck. And what you find when you do this exercise is that the orientation of the linear H1 structure, linear atomic hydrogen structures, is very, very well correlated with the plane of sky magnetic field orientation that we measure in either the polarized dust emission or the starlight. So this image is showing you in the top panel, the swirls, the brush strokes here, are the local orientation of neutral hydrogen emission structure. What is the orientation of the linear structure everywhere in this image? Bottom panel is showing you the plane of sky magnetic field orientation implied from the Planck data. Both panels have the same little white sprinkles on them. Those are the optical starlight polarization measurements. Those are largely tracing the same magnetic field that we observe in the dust polarization, with some differences in particular because the starlight polarization probes the path from you to the star instead of from you to infinity. And so this is exciting. This really points to excuse me, a new handle that we can get on the structure of the magnetic field from the gas emission morphology. We want to understand why these two things are so extremely well correlated. And a few years later, I did something even stranger. I was really curious about the structure of this emission as a function of velocity along the line of sight. So I just asked myself, like, if I measure the linear orientation of structures in a channel map of the H1 emission, so in a map of in an image of the emission integrated over a few kilometers per second in velocity, and I just do that for a bunch of different channels along the line of sight, I thought in my head that maybe how ordered or disordered the H1 orientation was along the line of sight and velocity axis actually might tell you something about the tangling of the magnetic field along that line of sight axis that you can't directly access otherwise. Excuse me. And so what this image is showing you is that appears to be true in at least the diffuse high galactic latitude ISM. This is showing you on the bottom panel that exact quantity. So measure the orientation of linear structure in H1 emission and along the line of sight and velocity, and just come up with a really simple metric for how ordered or disordered it is along the line of sight. Call that H1 orientation coherence, for lack of something that's not optimal. And then compare that to the polarization fraction of that thermal dust emission. And the fact that these two things are correlated is immediately telling you that much of this variation in the dust polarization is due to the geometry of the magnetic field, either within your beam or along the line of sight, or both. Because the H1 presumably is the only information that it has that's relevant here is about the structure, the local geometry of the magnetic field. With me? Huh? Okay, awesome. And a few years ago, Brandon Hensley and I sort of took these different pieces of information, of empirical evidence of the ways in which the neutral hydrogen structure is correlated with the polarized dust emission. And we put together this model, is a okay word for it. We put together this idea that we could describe these correlations in terms of a mapping between an idea we have about what's going on in real three-dimensional space and our actual measurement space, which we define in the axes velocity and orientation. And the idea is basically this: we measure these H1 data fundamentally in 3 dimensions, right? 2 spatial dimensions and 1 dimension of line of sight velocity. We measure PPV cubes, position velocity cubes of the emission data. And we can also measure the local orientation of these neutral hydrogen structures. And so our thought was that if in real 3-dimensional space, what you have going on along a particular line of sight are distinct regions of gas that is sitting in a particular magnetic field, that in general, if these magnetic fields are oriented differently, the gas emission from these 2 different regions will tend to map to different regions in orientation space. If the local gas tends to be, structures in the local gas tends to be aligned with the local magnetic field, which seems to be true, right? So we can define this mapping of our data, where here I'm plotting radially just the line of sight velocity. At what Doppler shifted velocity do we measure this particular emission? So red here is larger positive velocity, blue is larger negative velocity. That's just sort of a visualization choice so that the local standard of rest is always in the center of these images. And then azimuthally, I'm plotting orientation of linear structures in the H1 emission. And the point is that in general, emission at different velocities will, of course, map to radially different bins in the space, but also emission that is structured differently, that has a different orientation of its linear structures, will map azimuthally to different components of this space. And so for an actual sightline of data where we take channel maps of the emission along the line of sight and just perform this mapping of the H1 intensity into this velocity orientation space, it looks something like this. So we're not drawing a boundary here and saying this is a cloud, this is another cloud, and let's see how they work. We're purely defining this geometric mapping in the data themselves. And this appears to work the way we think it should to describe trends that we see in the measured dust polarization. So for example, if I take a sightline that has a very high fractional polarization dust emission, what I tend to see is that the H1 structures are very collimated in orientation space, even when they're fairly spread out in velocity space. Whereas if I take a very depolarized region of the dust, I tend to see more disparate structures spread out in this velocity orientation space. And I promise that I didn't just cherry pick the 2 pixels on this Planck map for which this story works out. This is statistically true over all of the data that we have. And so once you have defined this geometric mapping into your velocity orientation space, you're just a very simple geometric decomposition away from having something that is akin to the Q and U Stokes parameters that define linear polarization, except now this is just a measure of the H1 orientation as a function of velocity in your map, right? And weighted by the local intensity of the H1. And so that means that we can make maps of the Q and U Stokes parameters that are just a geometric description of the linear H1 structure as a function of velocity in your data. And then, of course, we can integrate over the velocity axis and have something that we can directly compare to the measurements we have from Planck of the polarized dust emission. So on the left-hand side here, I'm showing you these maps made solely from this geometric mapping of the H1 emission. So these are top to bottom Stokes, Q, and U. And then a different way to present these data are the plane of sky magnetic field orientation and the polarization fraction, which on the left here is really just disorder in the H1 orientation along the line of sight and or within your beam. And on the right are the same quantities that are actually measured in the dust emission. And so the point here is that we can compare this thing that is pure geometry and this thing that is actual measured physical dust polarization. And to the extent that these two things are correlated, that's coming again from the geometry. So just to go back to this point about the line of sight magnetic field hanging that I made earlier, if you looked at this all sky map of the dust polarization fraction, and you didn't know anything else, you might think that a lot of the variation here, you could come up with lots of different physics that could describe or drive this variation, right? You might think, oh, well, maybe there are some regions of the galaxy where the dust grains are less efficiently aligned or more efficiently aligned, and that is driving how fractionally polarized this dust emission is. But of course, to the extent that the large scale structure here is well correlated with this H1 geometrical tangling thing, you immediately know that that's driven by the geometry of the magnetic field, right? And not something like the polarizing efficiency of the dust grains. And so this gives you a comparison point to ask different questions of the data than we could with the Planck data alone. And these questions can be your questions because these data are all publicly available on this Dataverse. And really, I think this gives us a new way to analyze some of the properties of the polarized dust emission, or could otherwise be mysterious, and a new way to ask questions about the 3D structure, in particular, the line of sight structure of the magnetic field. And keep in mind that this third dimension here is velocity, right? This is not distance. I'm not saying that there is a one-to-one mapping between velocity and distance. What I am saying is that from the perspective of the polarized thermal dust emission, you actually don't necessarily care what blob of dust is behind what other blob of dust. You're always stuck with the line of sight integrated view. And this lets you pick that apart and have a hypothesis for how things might be varying along the line of sight based on the structure of the H1. We've done all sorts of fun things here trying to pick apart some of the correlations of different quantities that we see in the polarized dust emission. I've been very inspired by some of Kevin Hevenberger's work on sort of similar questions. about, this is a slide that's just a little bit for the CMB cosmologist interested part of the crowd. But particular correlations that we see in the polarized thermal dust emission, now we can ask questions about how the relative geometry of the density structures in the ISM and the magnetic field structure in the ISM might be generating what we observe in those quantities. And I have actually recently graduated PhD student who used this actually to great effect to really add, now we have a way of translating from H1 data to some idea of what the polarization structure might look like if the H1 and the actual polarized dust emission are related in a particular way. So we can build that model, compare it to actual dust polarization data, and then sort of iterate and ask what's actually the optimal mapping from H1 morphology to dust polarization, and why does it work like that? And in the process of doing that, George built machinery that could take basically any image and turn it into a polarization image by translating the linear structures into the local polarization field. The Stanford in E-mode polarization. That's something you were hoping to see today. And there's another piece to this whole puzzle, which for a time was not entirely clear, but now is actually quite subtle. And sorry about that Zoom thing, but the structures that are driving this magnetic alignment that we observe in the H1 are preferentially the colder phase of gas that we trace with the H1. And this is a statement that I'm basing on actually a number of different ways of asking this question. But the line widths of the H1 emission, the ratio of the far infrared to total H1 column, the morphology of this emission, as I'll talk more about in a minute, even though sodium-1 absorption toward these structures in the H1 are all consistent with these little filamentary, elongated, linear, anisotropic structure being preferentially cold relative to the rest of the H1. And so just to remind you of the big picture here, when we measure this 21 centimeter emission, we're tracing multiple phases of the ISM. We're measuring emission that is coming from the thermally bistable neutral medium of the ISM. By thermally bistable, I mean that at constant pressure, you can have two stable points in your equilibrium curve that appear to coexist in the ISM. And so we call these the warm neutral medium, for the W and M, and we call the colder, denser phase the cold neutral medium, C and M. And the gas appear to be partitioned into these two phases with some actually substantial fraction of the H1 emission originating from some thermally unstable phase that's in between the two. The point being here that we're talking about neutral gas, but that neutral gas itself is multi-phase. And we want to understand, just fundamentally in the ISM, how it is that warmer gas is able to, through turbulence and the thermal instability, form the colder phase of the gas, which is also, of course, the sort of precursor material for molecular clouds. And this is not a new question at all. There's lots that we don't understand about the way that the phases of the ISM are structured. and interact physically with one another. And one window that people have used to study this question is morphology. Because when you're always stuck with the line of sight integrated images of the sky, one way you can ask, do these two tracers know about each other, is to look for regions where you see a similar morphology in two very different tracers of your emission. And so people have done this with lots of different data, actually, in many different wavelengths. And this has been sort of fruitful for starting to put together a picture of how the ISM phases are distributed. And so we are asking a similar question here, but we want to do this not by looking at a patch of the sky and saying, hey, that kind of looks like this other thing. We want to come up with a quantitative description of the morphology of H1 emission that lets us probe whether the information about the H1 phase structure, how much of your gas is in cold versus warm phase, how much of that is encoded in the emission morphologies. And if that's the question you care about, of course, the gold standard way to do that is to forget about emission entirely. Find yourself a nice, bright background radio source, like a quasar, and measure the H1 absorption toward that source. What you really, really want is H1 emission and absorption toward approximately the same sight line so that you can more directly constrain thermodynamic properties of that gas. But of course, those sight lines where you can do that are sparse. You're limited by, you have to have your nice bright background quasar and actually make this measurement there. What we would like to do is understand what's actually encoded in the emission alone, right? And so we're going to quantify H1 morphology and compare to absorption line measurements where we have very good determinations of the mass fraction of the gas that's in the cold phase. And to quantify the emission morphology of the H1, we have used something called the wavelet scattering transform. A little complicated, it's actually very simple. We take some image, in our case, a channel map of the H1 emission, and we have some suite of wavelet filters with which we convolve that image. And then we can take a modulus and a spatial average and have ourselves a set of coefficients that describe sort of a first order morphology structure. But then we can take these wavelet convolved images, take the modulus of them again, and then convolve them again with our suite of wavelets, which are just filters that are at different scales and different orientations with respect to our image. And now we have a set of coefficients of numbers that describe basically the interaction between two different scales and orientations in our image. And so if this diagram is reminiscent to you of a convolutional neural net, that is not a coincidence. This was invented by mathematicians to dig into the questions of how it is that CNNs work. But for our purposes, this is a way of quantifying spatial structure in images that does not rely on any training, that does not rely on any particular learned filter set, that just starts with this very standard set of orientations and scales, but then can probe fairly complicated spatial structure as we get to higher order statistics of how the structure interacts on different scales and orientations. Does it make sense? Okay, so this is great for condensing morphological information into a more tractable set of values that still describes complicated structure in the image. And to give you just a sense of how this can work, we can, for example, take some image and then crank up a particular coefficient or set of coefficients and synthesize a new image, good old gradient descent here, that respects new increased coefficient that we want to probe. So for example, here's just an image of H1, and here we are increasing the power in wavelet scattering coefficients that are at orthogonal orientations to one another. You can see that as we do that, the structures become sort of fluffier. There's more power in orthogonal orientations. Here we're doing the opposite. We're cranking up wavelet sets that are parallel to each other in their wavelet orientation at two different scales. And so we're getting more sharp and elongated structures when we do this. So this gives you sort of a more intuitive sense for how it is that these particular coefficients are describing image structure. And then what we want to do is do this on a whole bunch of patches of channel maps of the H1 emission, and then compare it to the actual measurements that we have of the CNM mass fraction. So just how much of your mass is in this cold phase of your H1. And what we find is that the morphology of the H1 emission is really nicely correlated with the measured CNM mass fraction. In particular, a distillation of these coefficients that strongly correlates with the CNM mass fraction is this parallel structure that is parallel across different scales in your image, which is sort of consistent with these stringy, elongated filamentary structures being preferentially CNM. And in fact, the fluffier, blobbier stuff that has higher power in the orthogonally oriented wavelets at different scales, that stuff is actually anti-correlated with the mass fraction of CNN. And that's really just one particular distillation of this. There's really rich information in the spatial structure of the H1 that's correlated with the mass fraction of CNM in ways that we don't necessarily yet have stories to describe. And I think that's a fascinating line to continue exploring down. What we also want to do is see how far we can push this to actually make phase separated maps of the H1 emission, to actually start to study the phases of the H1 from the emission alone. And so this is ongoing work led by my grad student, Milky Way, where our contention is basically that there is information in the spatial structure of the emission about the phase. Everyone, always, forever, has, if you want to divine phase information from H1 emission, has only done that spectrally. Fit Gaussians to your emission spectra or something very similar to that. To the extent that there's orthogonal information in the spatial dimension, clearly the optimal thing is that we should be using both. But we are seeing right now how well we can do component separation on the structure of the H1 emission from the spatial structure alone. And then of course, the grand scheme of things will be to combine that with the spectral information and make the absolute best determination of the phase structure of this neutral gas in the ISM. And I want to make one more point to you, I think is pretty cool, because I've been secretly this whole talk actually setting up a bit of a mystery to you, which is, I think that there is really, really non-trivial information in the combination of a few things that I've just told you about. In the phase structure of the neutral gas in the ISM, which we have various ways of probing now, in this very tight correlation that we observe between the structure of apparently predominantly CNM, the colder phase of the H1, and the polarized dust emission, and of course, the beautiful measurements we have of just the dust polarization properties themselves. And I want to motivate this question to you with a hopefully unobjectionable statement, which is that any sightline that I have, I can describe in any sightline that I have through the neutral ISM I can describe in terms of a fraction of the column that's associated with the cold neutral medium and a fraction of the column that is not, right? And here I'm talking specifically about the neutral diffuse ISM. And by diffuse, I mean column densities of less than 4/10⁻20 or so. This is where the H1 and the dust are very good tracers of one another, in particular the H1 column and the dust total intensity are very tightly correlated. You haven't started to deplete much of your hydrogen into the molecular phase, for example, as you do at higher columns. So diffuse, high galactic latitude, neutral ISM. My contention to you is that a cartoon model of the magnetic field structure in the CNM column versus the not CNM column is probably not this cartoon that I've just drawn. This is a cartoon that I think is not representative of the ISM. This is a cartoon where the CNM column has some mean magnetic field orientation that is completely different from the magnetic field orientation in what is the bulk of the column, the not CNM component of the column. Generically in the H1, it's some combination of the warm neutral medium, this unstable gas, but just think of it as everything else, right? If this were the picture, the dust polarization angle that we measure would be really hard pressed to correlate so well with the orientation of these CNM structures in the ISM, right? And so instead, I think we should ask ourselves, well, if we have some mean orientation of the magnetic field in the CNM that's giving rise to some mean polarization fraction of the emission that originates from that fraction of the column, let's just ask ourselves what the data constrain for how much tangling of the magnetic field could be going on in the rest of the column. You can imagine two super extremes, which is everything is doing exactly the same thing. The magnetic field does not care which fraction of the column it is encountering along the line of sight. Or there is some dispersion of the magnetic field orientation relative to the component of the magnetic field associated with the CNM column. These are sort of two extremes, but they give us some phenomenological picture of what we might look for, right? In this first picture, there's a very high dust polarization fraction, actually problematically high dust polarization fraction if it's the cartoon I just drew, because the observed dust polarization fraction is, we have actual measurements of it. And in the lower cartoon here, I've drawn a magnetic field orientation that's just totally whatever it wants to be in the non-CNM component of the column. And here we should make a prediction that the FCNM, right, the mass fraction of the CNM is correlated with the polarization fraction of the dust, right? And that is what we find. We find that in the diffuse ISM, the dust polarization fraction is correlated with the CNM mass fraction, positively correlated. It's actually anti-correlated at high column density, but I don't have about that. And this is true even where the dust polarization fraction is uncorrelated with the total H1 column, the result that we've known since the work of Planck very, very nicely. And so we put this together into a very, very simple model. I mean, basically the Bayesian hierarchical model that describes this cartoon, and came up with a constraint on the degree of magnetic field disorder between the dust column that's associated with the cold neutral medium and the rest of the column, the warm and unstable components of the column together. And what the data seem to fairly strongly prefer is a more magnetically ordered, or is a picture that's consistent with the more magnetically ordered column of CNM that forms out of a more disordered column of WM. In other words, the geometric depolarization in the dust associated with the non-CNM fraction of the column seems to be higher than in the CNM associated fraction of the column. And that's what gives rise to this nice positive correlation with ISM, where if you have more CNM, you have, or more of your mass in the CNM, you have a higher dust polarization fraction that you measure. Okay, so this I think is actually really, really non-trivial, and I want to understand fully what this is telling us about the physics of the ISM. Because the thing to keep in mind here is that my little cartoon here of the two columns, this is to scale in terms of typical fraction of the column in the CNM versus the WM. Absolutely not to scale in terms of the three-dimensional volume that those two phases occupy. We're probing with the CNM structure a much smaller path length through the ISM in general than in the warmer, more diffuse media. And so what is this telling us about the three-dimensional structure of the magnetic field? What can this tell us relative to predictions for multi-phase numerical simulation? These are the questions I'm really keen to answer next and would love to discuss with all of you. But let me just leave you here by saying that I hope I've convinced you that the morphological information in our ISM tracer is really rich in terms of what it can teach us physically. We've shown the H1 in particular can help us probe three-dimensional magnetic field structure and the phase structure of the ISM. We've used that to put what I think is pretty qualitatively new constraint about the relative magnetic field disorder between regions associated with different phases of the neutral ISM. And now we need to figure out what else that's telling us about the physics. And stay tuned for more in this vein. Thank you.
Time for questions.
So one question I had was in the H1 based models for QU.
Yeah.
The intensity that you use, that's also the H1 intensity.
Yeah, exactly. Yeah, so here. Yeah, this is weighted by the local H1 intensity in each
So
channel.
it's purely H1 on that.
Purely H1, exactly. Yeah.
The overall normalization compared to wanted to make that into just I guess you have some empirical normalization.
Yeah, exactly. And so here, here we have not actually done that, right? These color bars are up for the H1 side, they're still in Kelvin kilometer per second. And then we're just comparing morphology to the more Kelvin CV in this case. But you absolutely could, and then you could start to ask yourself, you know, if I weight differently the ways in which these data are related to the dust intensity, you know, do I get better or not? That's also an interesting question to ask in the context of this modeling that we're doing with the phase structure relative to the dust polarization. Because one way that you could have that be less of a constraint on the geometry of the magnetic field between the phases is to have a different dust emissivity for dust that's associated with the cold phase of the ISM versus the warm phase of the ISM, right? You don't have a ton of wiggle room there, and we argue in the paper you're actually very constrained by other data there, and so we argue in the paper that can't explain the effect that we see, but that's something else that you could throw in as an ingredient to that model if you want to.
Yeah, the analysis to me is really compelling at the end, but I'm scratching my head. If the cold neutral medium was truly totally neutral, you won't feel the magnetic, you need some ionization.
Right.
So it kind of goes the opposite way you'd expect. The warm medium is going to be probably have a higher ionization, so I can get through that.
Yeah, good. Well, you're absolutely right, right? The whole reason that we have this magnetic alignment to begin with is that the neutral medium is not fully neutral, right? And I mean, I think the fairly straightforward answer is that even at 10⁻⁴ ionization fraction, that's enough to couple you to the magnetic field. That will do it. And so in that sense, I don't think that we should be terribly surprised. Yeah, and then it just becomes a question of, okay, how much disorder do I have on these very different scales in these different phases? And I think that's actually the key to
Do
understanding.
you think the lack of order in the warmer phase is probably turbulence or something like
Yeah, I do. Yeah, the picture I have in my mind right now that I want to, test more is that the way that CNM forms is that you have a turbulent, warm gas region that has little pockets that are compressed and able to undergo thermal instability in order to form these little pockets of CNM. And that in that process, the magnetic field on the scale of the mass that's being condensed into this little colder pocket is now more uniform on that scale, right? Relative to the diffuse item. That picture is consistent with the data that we're finding. And it's funny, I depending on who I talk to about this, depending on who in the plasma turbulence community I talk to about this, they're either like, oh yeah, it totally makes sense. Like that's the cartoon I have in my head too. Yay, we agree. Or they're like, this is completely not at all how I picture this process. And I would have guessed the opposite result. So I think actually there's real constraining power here for our models of the cold gas formation and for our models of what the magnetic field has to do with that process.
Seems like, oh, sorry, no, you can go ahead.
Okay, so you use these wavelet transforms, right? So we can use them for constraining the non-Gaussianity of the test maps also, right?
Yeah, totally.
Did you do that also? Are you thinking in that direction also? Because
I have been thinking in that direction. I think you're probably a perfect person to talk to about that direction. Yeah, absolutely. I mean, we are part of the point here, right? Is that the information is it's just not in the power spectrum, and this is, I think we've shown convincingly now, like a way of reducing the data into something that retains information about the not Gaussian structure that we care about, but is also, compact enough to deal with. It's not pixel space information anymore. And so, yeah, I think this is actually, if you were interested, for example, in modeling the small scale dust polarization structure for whatever reason, maybe because it's a foreground to your CMB experiment. I think this is actually a really promising direction to go, to characterize the structure of the non-Gaussian structure with a wavelet scattering transform like this. And then use that, basically make a scale invariance argument to generate structure on the scales that we haven't measured well in the dust polarization. Yeah. So if you're interested in working on that, I think that's absolutely something to do. And yeah, I think that's the right thing. I think that is the right way to do this. This is how we should build that sky model for.
yes.
Yes, great.
So I was gonna ask, it seems like if I understand things correctly, right, that most of the correlation, with the dust polarization is coming from what I would call essentially like higher density filamentary structures in the H1 compared to the bulk of the H1. So I guess one question is, would you expect even stronger correlations like with a CO map, where now you're even looking at even less turbulent, you're even more dominated by these much more coherent structures, or does this stop working?
This is actually a really interesting question. I mean, I will tell you that when I was first doing this, right, I was really focused on the diffuse ISM, where I knew that the dust and gas are tracing each other really well. By the time I decided to do this, I was like, well, I have made this algorithm and my code's really fast, should do it for the whole sky.
But I expected to see very clearly that the correlation would drop as you got to lower galactic latitudes for exactly that. I think that the reason you don't see a total breakdown at lower galactic latitudes is basically the scales that we're tracing here. This is at like 80 arc minute resolution, limited by the fidelity we have with the Planck data. But people have done really detailed studies of the magnetic field orientation in relative to structures in CO, and it's a complicated story actually, because it's not always that your structures are aligned with the magnetic field. Once self-gravity of your object becomes important, you actually can pretty often have this situation where the denser like the denser CO filament, for example, is orthogonally aligned relative to the local magnetic field orientation. Yeah, but it's a great question. And I actually think that particular question is something to explore more, and what we really need are observations of the magnetic field on the cloud scale in these molecular clouds. These data are fantastic. It's a bit too low resolution for the way you'd really like to do that. And so what you would really love are large scale maps of the far infrared polarization, high angular resolution. Gotta go to space. So the Prima mission would be fantastic for this, right? And from the ground, we will do some of this with SO and with the Simons Observatory, and hopefully also with CCAT, which is getting up to higher frequencies. I can do a bit of that.
Thanks, Susan, again.